More news of progress in the field of science and technology. We have another live report on BBC1 from Tomorrow's World.
And welcome. Take 1 can of checkered paint, put it in a spray gun, and now I can spray a checkered pattern. Don't believe me? Right. How about that? Well, of course, this isn't really magic. If you want to find out how it works, you'll have to stay tuned.
And later, I look at a seemingly magical way of stopping sewers overflowing. We investigate whether this Scottish island is now safe. And we describe a new test which should make screening for cervical cancer cheaper and more effective. But first, it's up to Howard.
Sorry, we seem to be a bit behind ourselves this evening. Still, these scaffold towers are perfect for doing jobs when you're up here, up in the rafters. Well, that's number 66 done. My next one, I think, is number 85. Ah, well, that's right over there. How on earth am I going to get myself across to the other side?
Shall I take you down there?
Yeah, could you?
Yep.
What do you mean you'll pull me over?
The thing is, Howard, I'm wearing the right shoes.
Oh, yeah?
Had you read your papers this morning, you'd know all about it.
Oh, I see.
Because the shoes are not on my feet, but on the base of these scaffolding poles. And they are little hover pads. And what that means is that the whole structure is just hovering about 3 millimetres above the studio floor. So it's ideal for use on any flat surface.
Well, thanks, Maggie. I'm really moved. Well, underneath those hover pads, air is pumped in here. That inflates this skirt, and then air bleeds out of this centre section to form the cushion on which the whole thing floats. And this shoe has been specially designed so that the hover pads can simply slide in or out. And 4 hover pads, 2 sets of shoes, and the whole lot will lift 12 tonnes.
Happy? Right, when you're in the right position, all you do is shut off the compressed air, and the whole thing settles down gently to the ground. That do you?
No, this isn't quite right, Maggie. This is 85. We needed 185.
Now, ever since we showed you the first portable personal stereo in 1980, entertainment equipment has been shrinking. A couple of years ago, we saw the sound and vision version. The first pocket colour television using a 2-inch flat liquid crystal display. And there we are, there's Howard still up in his tower. Then came the smallest video technology yet, a tiny cassette tape, which provides feature-length movies and concerts, as you see here. So, what's next? Well, put these two together and you get this, a travelling video. Let's have a look at it. It plays the same small Video 8 cassettes and displays the picture using the same liquid crystal technology as the Pocket TV. But with some important improvements. It's brighter, better colour and 1 inch larger, which is impressive because this is one technology where the challenge is making it bigger. That's always been difficult because of the way the picture's controlled. In the screen, there are thousands of tiny colour elements, magnified 500 times. This is the actual screen working. Each colour element must be switched on or off in turn to build up the full colour moving picture. And that switching is achieved by the screen's liquid crystal layer, which acts like a shutter behind every element. Now, normally it lets light pass straight through, as it is doing here. But when a voltage is applied, it blocks out the light. Let's just try that again. There, it's blocked out. No voltage open, voltage on, and it's dark. But to keep it closed, the voltage must be maintained. And in practice, that's done by a transistor. In fact, there are thousands of shutters, one for each colour element. And there's a transistor built in at the back of every one. You can just see the transistor here. It's the rectangular shape at the top left-hand corner of each element. Now, altogether, it takes more than 89,000 transistors to control this 3-inch screen. To add an inch and maintain the detail, you'd need another 60,000. And if any one fails to work perfectly, you'll get a hole in the picture, which is why this is such an achievement. It's extremely difficult to manufacture completely reliable transistors uniformly across this sort of area. So, until now, liquid crystal screens have slowly increased in size, inch by inch. But we could soon see a dramatic increase in the size of flat screens, thanks to a new type of liquid crystal, which gets rid of transistors altogether. In this prototype, which is British incidentally, there's just a layer of the new liquid crystal between thin sheets of glass. At the moment, the crystal is in the open position. Apply a voltage, moves to the closed position. But the difference with this crystal comes when I remove the voltage. It stays closed, as you can see, on, still closed. Whichever way it's switched, it will stay, because this liquid crystal has 2 stable states. There's no need to maintain the voltage, and so no need for transistors. I know that screen does look primitive, but it's taken the researchers years to get this far, and they expect to achieve something about this size in 5 years' time. But while you're waiting for that at home, you may be given one of these while you're travelling. Already, airlines are interested. So on those long flights, rather than a movie you don't want to watch or don't want to watch again, you could have your choice, or even bring your own.
It's been like this all morning. Not a thing. And I was relying on this fishing trip to get me lunch. Mind you, I think I'd catch a better bite over there. But there's one small problem: how to get across the river. Of course, if all else fails, I could simply walk across.
So there we are, 20-metre bridge, completed in just 30 seconds, simply blown up with compressed air. It's going to be particularly useful in emergencies for rescuing people or even animals in floods or from thin ice. Of course, it's quite handy for crossing a river if you're in a hurry.
That's better. They say that this bridge can carry up to 20 people at any one time. And if you need to go further, then you can simply extend it up to 60 metres.
Oi! Who left that here?
This year in Britain, 2,000 women will die needlessly of cervical cancer. And I say needlessly because it's the one cancer which is completely preventable. A crucial part of prevention is mass screening, which has already reduced deaths in Canada and Scandinavia by up to 90%. But here in Britain, over the same period, deaths have only been reduced by about 19%. However, some important new research now offers hope that screening here in Britain could be dramatically improved. Women need to be regularly tested so as to catch the disease in its precancerous stage, when it can be cured by simple methods. Last week, the government asked health authorities to increase their screening programmes so that women are tested every 5 years from the age of 20 instead of 35. But most experts feel that this 5-year gap between tests is too long. What's more, no specific funds have been allocated for the additional workload. You see, when your smear test arrives at the lab, it has to be checked visually for the presence of cancerous cells. And what they're looking for are these enlarged nuclei there. But you just think about it, they have got literally millions of cells on every sample to check. It's a difficult and painstaking progress. And there are considerable backlogs in some of the labs. Well, scientists at the Whittington and Royal Northern Hospitals in London have now developed a completely new approach to smear analysis, which could be both simpler and cheaper. It looks as though you can detect the disease through the chemical changes in the cells before there are any of these visible changes. And the key to this lies in what are called free radicals. Free radicals are highly unstable charged molecules which occur naturally in our bodies all the time. They only exist for microseconds, during which time they damage the molecules around them, which sets up a chain reaction of damage. A cell membrane is made up of lots of different types of fat molecules called lipids. And if these are damaged by free radicals, they change their chemical structure. In cervical precancer, the cells seem to have an unusually high percentage of one particular type of damaged lipids, the 9,11 linoleic acid. Now, you can't find these under a microscope, but you can detect them chemically using some very standard technology, this chromatograph. And this uses ultraviolet light to analyse the different lipids in each sample. And if you just take a look at this printout, what we've got here are several samples, but we'll concentrate on the two at the end. Now, the first one is a healthy sample, and note first the level here of the red trace. Now, that's the 9,11 lipid, and you can see it's very much lower than the level of the adjacent 9,12 lipid. Now, let's just compare that to a precancerous sample here. Now, immediately you'll notice that the level of the 9,11 lipid has shot up here. It's very much higher than the 9,12, and it seems that the higher that the 9,11 lipid rises, then the more advanced is the disease. Now, there may be an important clue here for all cancers, because for some time it's been believed that it may be that free radical activity which is involved in the triggering of a cancerous change in cells. But as a screening test, this system is already undergoing trials. So far, it's proved itself very accurate, and it's certainly cheap and simple, and very much faster. And perhaps most important, these tests pick up the cancerous changes at a much earlier stage. If this system can be used around the country, it will be of crucial help to the screening programme. And there are 2,000 lives which could be saved. Now, Judith.
This is Portland Square in the heart of St Paul's, Bristol. In the Victorian times, this square, with its elegant Georgian buildings, formed the core of the district. But the century has seen inevitable development, and more people living above ground can cause havoc down below. Like all Victorian sewers, this one wasn't built to cope with the 1980s and all the extra sewage. It only takes a downpour for this to fill up and overflow. Now, this overflows into a local river, but some sewers do overflow into gardens and even houses where sewage is definitely not welcome. But it would be too expensive to replace all the sewers, which are liable to flood. So a way of solving the problem without rebuilding has been pioneered here in Bristol. And the solution at the moment is standing about 200 metres upstream. It's a mobile unit which uses an ultrasonic sensor hanging in the sewer to monitor the level of sewage. And if it reaches a critical height, the machine automatically releases a chemical through the manhole and into the flowing sewage. It starts life as a white powder made up of long coiled molecules of polyacrylamide, which are first mixed with water. The chemical, which is quite safe, has a lubricating effect, reducing friction and drag between the walls and the sewage. It also produces a smoother flow in the sewage itself, allowing it to flow faster and so prevent flooding. We checked the weather report before we came down here today, and we're not expecting rain, so we're not expecting the sewer to fill up. There's no way we'd be here if we did. But we are going to release some of the polymer, and we're going to release it along with some purple vegetable dye so that we know when it arrives. First of all, I'll check the flow at the moment. It's flowing at about 0.5 metre a second. And I think I can see it's purple at the moment. Yes, the polymer's coming down. We'll take another reading. Yes, I can see that's speeded up quite a lot. 0.7 metres a second. That's an increase of about 40%. On a bad day, when the sewer fills up, that means it would drain away an extra bathful of sewage a second, which would prevent a very smelly incident up above. If you're unlucky enough to live in one of the thousands of homes in Britain where sewage regularly overflows, you'll have to keep your fingers crossed that a mobile unit turns up over a manhole in your district. It could be very sweet news.
Results published today in the journal Nature suggest that the delicate layer of ozone in the upper atmosphere that shields us from harmful ultraviolet radiation is under even greater threat than was thought. A few years ago, British scientists flying sensitive instruments on balloons above Antarctica found a hole appearing in the ozone layer each October. Studies from space show that the hole, in blue and pink, is growing year by year, and last year spanned the whole Antarctic continent. The latest American measurements show that about 10 miles up, just where there should be most ozone, the level had actually fallen by 90%. Well, this almost certainly reflects a worldwide decrease in ozone, which could lead to changes in the climate, major crop losses, and a substantial increase in skin cancers. The culprit is most probably chloro or fluorocarbons used in aerosols and fridges, which the Americans banned in 1976. Last week in Vienna, US delegates harshly attacked Britain and France for failing to follow their lead.
This week has seen two international developments in the search for other intelligent life in the universe. It's generally been assumed that life would develop on a planet something like our own. But so far, not a single planet has been identified anywhere in the universe outside our own solar system. Planetary systems start off as a cloud of dust and gas orbiting around stars like our Sun. New data from a satellite carrying out an infrared survey of the sky has shown the existence of clouds around 6 stars. It's the first confirmation that planetary formation is probably quite common. Meanwhile, the Russians found radio emissions coming from the region of 9 stars. Our radio and television signals are leaking out into space, so this edition of Tomorrow's World will be reaching Alpha Centauri in about 4 years. If ET is out there, we ought to be able to detect his transmissions too. Unfortunately, there's no indication so far that the Russian radio sources aren't just naturally produced.
This week, the successful results of a remarkable experiment in genetic engineering were announced. Scientists were trying to cure mice with an inherited genetic defect, in which, because a gene is missing, the nerves develop incorrectly, so the mice shiver uncontrollably and die young. To overcome this, the researchers managed to isolate the missing gene and make hundreds of copies of it. Around 200 copies were injected into a fertilized but defective egg, which would normally produce a shiverer mouse. By an unknown process, some of the gene copies are inserted into the mass of ordinary mouse genetic material. As a result, in one case, the shivering genetic defect was cured. It's the first time ever that an inherited nerve disease has been cured by genetic engineering. Now, although there are many inherited diseases in humans, the process is still far too random to be used in human embryos. But it is likely that this type of gene insertion may be attempted in affected adults in the not-too-distant future.
You've probably heard the many rumours about alligators living in the sewers of New York and other cities. But can an alligator live in a sewer? Well, this week, technicians checking out sewers in Orlando in Florida found out the real answer.
And we watched him for a moment to really determine whether it was an alligator or just a log in the line. And then he opened up his mouth a little and smiled at us, and that was enough to determine he really was an alligator.
A local alligator expert, Mr. John Tanner, disappeared down the sewers shouting alligator mating calls, armed only with some strong tape. And it wasn't long before the remarkable Mr. Tanner re-emerged, hauling the alligator with him, solving one of the great unanswered questions in alligator natural history. And by the way, he let it go in a nearby river.
From alligators to insects. Although these wings do look extremely colourful, They contain no colour pigment at all. They look like that purely because of the way light is reflected from their surface. And the same principle is used for this tamper-proof seal, which can be used to protect all sorts of things from drugs to chocolates. Now, once this tape is torn, the iridescent colour disappears for good. The tape itself is clear, and it's got this silver backing. And between the two are layers of incredibly thin, transparent films, each 20 times thinner than a human hair. And just like on the insect's wing, when light hits them, they reflect colour back, and the intensity of this colour is helped because of that silver mirror backing. The actual colour depends on the thickness of the films. That's why when you make a soap bubble, you see all sorts of colours there reflected. And that's because the thickness varies throughout the surface. But in this new seal, the layers of film are all the right thickness to reflect back just that one colour. So when these seals come into use next year, you'll have a very visible sign to tell whether anyone's been tampering with the contents. Now, here's Howard.
Inside this ordinary-looking building, scientists work with some of the most dangerous substances in the world. It's Porton Down, the Ministry of Defence's chemical defence establishment. Although the large-scale manufacture of chemical and biological weapons was banned in the late 50s, research is allowed and still goes on for purposes of defence. Behind the laboratory doors, people are working on nerve gases, blood poisons, choking agents, on chemicals that blister the skin, and on germs. For one of the CDE's current tasks is to deal with anthrax, the first and crudest of the germ weapons manufactured for the world's biological arsenal. Back in 1942, the natural disease, anthrax, was developed for use against the Germans. Planned targets included the people of 6 major German cities. At that stage, there was no vaccine. Inhaling the spores dropped in bombs would have caused death in days. The war ended before they could be used. But one legacy remained. Gruinard, a small island off the west coast of Scotland where the bombs had been tested. The farmers were taken off and sheep were landed to be the victims of the experiment. The island is still a no-go area. But last July, over 40 years later, in a strange reenactment, the flames were alight again. The MOD are attempting to rid the island of the disease. It's dangerous work. All the scientists had to wear protective clothing, even after a 7-month course of vaccinations. After burning off the vegetation, 30 miles of flexible piping were laid on the scorched earth to carry the decontaminating agent. Formaldehyde diluted with seawater was pumped over the ground, 50 litres per square metre, to soak the soil to a depth of at least 15 centimetres. 4 months later, samples of soil were taken from the treated areas. They should show that the island has been successfully decontaminated, because formaldehyde kills everything, including anthrax. It's one of the classic ways of sterilising the soil. So why has it taken so long to try it out?
The reason is it's taken nearly 40 years to find a technique that allows them to check just how much anthrax there is on the island and whether their treatment works. And it's been difficult because anthrax is in the form of spores. They're extremely tough and almost impossible to detect.
A core sample taken before the treatment could contain anthrax spores, but to detect them, scientists had to make the spores germinate to form active anthrax bacteria, and also make sure that no other bacteria would grow, or they'd hide anthrax. Exposing the earth to air and to heat in a water bath killed a vast number of bacteria. But the real art of the process lay in making a growth medium, a cocktail of poisons to kill off all the remaining bacteria except anthrax, combined with a group of nutrients to help the anthrax spores develop. One of the things anthrax needs to help it grow is, gruesomely, an ingredient extracted from animal blood. The samples of dirt from the island were placed on the medium and then left in a warm, dark environment to germinate. The defence scientists were waiting for the appearance of small, round marks on the gel, marks showing that a bacterial colony had grown. Anthrax, and here it is. The spores stain blue, germinating to form the rod-like bacterial growth. So at last a technique had been developed that meant the MOD could find out exactly where the anthrax was on the island. And they only found it in certain spots. Here where the bombs exploded, here where the sheep were tethered, and here where they were taken after being infected. And the discovery that the anthrax hadn't spread throughout the whole island meant that the MOD would only have to treat 11 of the 500 acres of Gruinard. And now the technique is being used to see whether the formaldehyde treatment has worked. A production line was set up and hundreds of soil samples are being analysed. The results will be officially announced in a few weeks, but it's almost certain that the island is virtually clear of anthrax. Though there are likely to be a few deeply buried spores left. And anyway, no test is foolproof. So they may have to land sheep again, this time to demonstrate that the island really is safe for people. But the long battle with anthrax isn't over yet. It'll still take many years for the animal and plant life to recover fully from the formaldehyde treatment.
So, here it is again, right before your very eyes, nothing up my sleeves, checkered paint. And it's red and gold this time. Now, as we said before, there's nothing magic about this. It's simply a very new paint, which is particularly useful for the tricky paint jobs like this, where paint manufacturers would want to paint these grooves a different colour to the rest of the panel. Now, normally what they have to do is to paint the grooves very carefully and then mask them over before they can spray the rest of the panel. Now, all they have to do is to do it in one hit, like that. There we are, blue with a silver inlay. The way this works depends on two things. One, of course, is the makeup of the new paint itself, and the other is the nature of the wood surface that you're painting on, in particular how absorbent it is. Now, the paint can be used on various things like ordinary hardboard or this, which is fiberboard. It's what a lot of modern furniture is made of. But before it's cut into shape, the board is given a spray of lacquer. Now, this gives it a smooth and slightly shiny finish, which is less absorbent than the untreated wood. Then, whatever pattern you want to gouge or route out, it exposes the untreated wood underneath. But how does that come out a different colour? Well, obviously, two colours of paints need two colour pigments. And if we look at two particles of pigments vastly enlarged here, you can see that the red pigment particles are smaller and lighter, and the gold ones are heavier and look more like this. And they're both suspended in a solvent. On our model here, there's the wood here with its layer of lacquer, that black layer on top. And if the paint is sprayed onto this area, then nothing soaks in through the lacquer. So therefore, the small and lighter red pigment literally floats to the top, completely covering over the gold paint. But here, in the roughened groove, the paint solvent soaks into the fibres, taking the small red pigments with it. So the gold pigment particles, which are too big to soak in, are left on the surface. So it looks gold. But what about the checkerboard? That wasn't routed out. Well, in this case, only a part of the pattern has been lacquered. One set of squares has been lacquered, while the other set has been left as bare wood. And that's the result. Clever, eh? Well, that's all from us for tonight, except that I have one further revelation to make. Till next week, good night. Oh, look at this.